Hey everybody, this is a lecture about measuring resistance. So let's start by just redefining resistance. We know resistance resists current in materials, but our definition of resistance is the ratio of voltage to current. It's volts per unit amp. So if we think about a 25 ohm resistor, what that actually means is that, well, that means the ratio of voltage over current is 25 ohms. So let's say I have 10 volts of voltage across that resistor. Well, how much current is that going to be? Well, I can just use I equals V over R. You can figure it out. Let's see. 10 over 25. We're going to get 0.4 amperes of current. Well, since it's 25 ohms, that ratio is going to be constant. So if I double the voltage, that implies that my current is going to be twice as much, 0.8 amps, and so on and so forth. 30 volts will be 1.2 amps. That's what a 25 ohm resistance means, that ratio is this specific value. And this is going to be true, this pattern is going to be true when we think about normal resistors. Normal resistors are called ohmic materials. And the word ohmic comes from Ohm's law, V equals IR, or R equals V over I. Ohmic materials have a constant resistance. So that means the ratio of voltage to current is constant, or current is always going to be proportional to voltage. And that means if we graph current against voltage, we're going to get a straight line that passes through the origin. It could look something like this, could look something like this, or it could look something like this. Since resistance is voltage over current, if we have more voltage for the same current, that's going to be a higher resistance. So this would be a high R, this would be a low resistance for ohmic materials. But we can also have, well, a lot of real materials are not ohmic. And in fact, real resistors are only ohmic under some range of currents, under some range of values. For example, we often model light bulbs as resistors, but in reality, in the light bulb, as the current increases, our material is going to heat up, and our resistance is going to increase because there's all that extra thermal energy, things are vibrating, it's going to be harder to get current through. Other materials and other circuit elements are also have non-constant resistances. Some common ones are LEDs, diodes, or anything very low and high temperature, bulb filaments, and transistors. So a lot of things used in electronics are actually not, they don't act like resistors. Their resistance is not constant. But we can still measure the resistance at different voltages or currents. And if we graph our resistances, we'll get something that isn't a straight line, it isn't a proportional graph. For example, with our diode here, we start out with, as we increase the voltage, we get no current, and then after a certain voltage, the current increases a lot. So our diode starts out with high resistance, and then the resistance is going to decrease over time, or not over time, at higher voltages. Our light bulb filament is going to behave the opposite way. As we increase the voltage, well, our current is always going to increase, but if we were to draw basically a line from here to here, the slope of that line, that average slope, gives us the resistance. And since that slope is decreasing in this case, we're getting more voltage per unit current. Our resistance is actually going up. And remember, for a resistor, for an ohmic material, it's just going to be a straight line, no matter what. So our resistance is constant. Now, one thing to keep in mind, resistance is not going to be the slope of this line. It's not going to be the inverse of the slope. It is really just the value of voltage over current. So it's whatever this value is here, divided by whatever this value is here, voltage, current. And we can find that at any given point on the curve. By the way, an LED is a type of diode. It's a digital input-output device. It only lets current flow one way, and also it requires essentially a startup voltage. So it starts out with a really high resistance, then a low resistance. So let's do an example. The graphs show the voltage current distributions for two circuit elements, X and Y. Are X and Y ohmic or non-ohmic? Well, yeah, let's just do them one at a time. Are X and Y ohmic or non-ohmic? So before we do that, let's look at the graphs. On our vertical axis, we have volts. On our horizontal axis, we have current in milliamps. So it's just a voltage current graph. It's not the same as the graphs that we saw before because those were current voltage, but we can still get resistance from it because R equals V over I. Are X and Y ohmic or non-ohmic? Well, X is a straight line that goes through the origin, so X is ohmic. Y is non-ohmic. For the non-ohmic elements, does the resistance increase or decrease at higher currents? Okay, so our non-ohmic element is Y. So we start out with some resistance like this. And as we go on, that line is not quite as steep. So that means we're getting less voltage per unit current, so our resistance is going to decrease. The resistance decreases over time. Another way to think about this, I'm going to erase these lines. Let's actually just reason through it. As we increase the current, eventually our voltage approaches a constant value. And current keeps increasing. So current keeps increasing even at a constant voltage, or as voltage just barely increases. That's going to be a decreasing resistance, more current for the same voltage. For ohmic elements, find the resistance. Okay, well, X is our ohmic element. To find the resistance, we just do voltage over current. So we want to choose one point on this line. It doesn't actually matter what point we choose because that ratio is constant. If we were to draw a line from the origin to this top point, it would pass through every other point on the line. To get our most accurate value, we want to choose a value that's quite far away from the origin. And figure out what the current is and what the voltage is. So the resistance of X is going to be the voltage over the current. Voltage is 6.246, 6.6 volts, over my current is 4.1234, 4.4 milliamps. 6.6 over 4.4, I think it's 1.5. So it's 1.5, and since we're dividing by milliamps, that's going to be the same as kilo ohms. 1.5 thousand ohms. Easy Ohm's law. For the non-ohmic elements, find the resistance at 1, 2, and 3.0 milliamps. Okay, so that's going to be for Y. Let's look at 1 milliamp. I'm going to just draw in these values here, 2 milliamps. My lines aren't perfect. And 3 milliamps. 3 milliamps. Okay, so the resistance of Y at 1 is going to be equal to voltage over current. That's going to be, looks like 3.8 volts over 1.0 milliamps. So 3.8 over 1 is just 3.8. That's going to be 3.8 kilo ohms. It's a higher resistance than X because it's above that line on this voltage current graph. Resistance of Y at 2, well, at 2 milliamps, that's right here, we're at about 5.2, 5.3. 5.3 volts over 2.0 milliamps. 5.3 over 2, 2.65, 2.65 kilo ohms. For 2 sig figs, it would be 2.7 kilo ohms. And the resistance of Y at 3 milliamps is, let's see, looks like it's about it's a little past 5.8. It's going to be about 5.85 volts over 3.0 milliamps. About 1.95 kilo ohms, or to 2 sig figs, 2.0 kilo ohms. So really, we just look at the graph and use Ohm's law to calculate the resistance. One last question is, what type, based on the graphs previously, what is Y most likely? What type of material is it? And it looks like, well, the resistance is decreasing at higher currents. So that means it's more likely to be a diode than a bulb filament. Could be an LED, could be a transistor, but it's some sort of diode maybe. Let's move on. Okay, so since we need a voltage and a current to get a resistance, we need a voltmeter and an ammeter simultaneously to measure resistance. And this is going to work for any circuit. If we know the voltage and the current at the same time, we can get the resistance. We don't need to necessarily calculate if we can measure. So for example, if we have a single resistor in a circuit, we're going to need an ammeter to measure the current through the resistor. Now, unfortunately, you have to open up the circuit and place the ammeter there. So it goes like this. That's in series. And we need a voltmeter in parallel. So I'm just going to stick a voltmeter here. It is in parallel with my resistor. The ammeter shouldn't affect the voltage drop across the resistor, ideally, because it has such a low resistance. Same thing here. This is a much more complicated circuit, but if you just measure the current and the voltage, that gives you everything you need to know. Stick an ammeter in series with the whole circuit. This is my whole resistive part of the circuit, and a voltmeter in parallel. Measure them both, then just use Ohm's law. Here we have a picture of a breadboard circuit, and a breadboard is going to have essentially one part of the circuit connected to the negative terminal of a battery, or negative voltage, and the positive terminal is going to be connected somewhere else. So if we want to measure the current, or sorry, the resistance, we just need an ammeter and a voltmeter. Ammeter always in series, voltmeter always in parallel with the circuit. Now keep in mind this is always going to work, but for example, for this circuit, the resistance will change at different currents when different things are going on. So you do need that voltmeter and ammeter. You can only measure the resistance in a particular state. That resistance can possibly change, especially since it's not a pure resistor circuit. So even though in general resistance can change, we know that for resistors, they're ohmic, so the resistance is constant. And we do have a special meter that's used to measure resistance called an ohm meter. And what an ohm meter does is it pretty much just combines a voltmeter and an ammeter into a single instrument. It applies a known voltage and measures the current, and then uses Ohm's law to calculate the resistance. The symbol is a circle with a capital omega in it to indicate it's measuring ohms. There are two terminals, just like any meter. And it's only going to give you an accurate reading for ohmic materials. That's materials that keep a constant resistance. Because essentially in order to connect this, because it's an ammeter and a voltmeter, you need to connect it in series and in parallel at the same time. The only way to do that is to take your resistor out of whatever circuit it was in, and then just connect it directly to the ohm meter. So this is how we connect our ohm meter. It forms its own circuit with whatever you're measuring the resistance of. You can't actually use an ohm meter in a circuit that's already built. It will not give you an accurate reading. And if you want to take a look at what's inside an ohmmeter, it's going to be something like this. There's going to be some voltage source, some EMF, some voltmeter, or basically some way to ensure that that voltage is constant, and an ammeter to measure the current. And then that's connected in series with a resistor. This works with normal resistors, but again, it doesn't work with things like LEDs, light bulbs, or diodes. Only ohmic materials. In summary, resistance is always R equals V over I, always. That's the definition. And it's constant for resistors, which are called ohmic materials. It changes at different currents for non-ohmic materials, like light bulb filaments, diodes, transistors. But it can still always be measured with V and I, because that's the definition. So if you stick a voltmeter in parallel with your circuit and an ammeter in series, then you can calculate the resistance. If you have a resistor, you can also measure the resistance using an ohmmeter, but you need to take it out of your circuit and connect it in technically both series and parallel with your ohmmeter. That's all.